Okay, welcome back. This is our fourth video on algebra and number theory, and today we're going to focus a little bit on elementary number theory. And so overall what we're going to do is look at the greatest common divisor, or GCD, and that is calculated via the Euclidean algorithm. Then we're going to use that to calculate modular inverses, and of course multiplicatively. And finally, we're going to look at the Chinese remainder theorem. Okay, so this is just an overview here. So first we have the quotient remainder theorem, which we use in order to calculate the GCD using the Euclidean algorithm. And that says, given that we have positive integers n and d, there exists a quotient and a remainder that are integers such that n is equal to d times q plus r, where r is between 0 and d but less than d. Now, when we have an n and a d that are positive integers, the way we calculate the quotient is we divide n by d, and then we take the floor of the result. So if you have something like 5 over 3, for example, you would divide that, get a decimal number, and so what is that? Let's see, it's 1.6 recurring. And so you would take the decimal part on the right of the decimal point and throw that away, and you would end up then with the number 1 as your quotient. Okay, so this is the greatest integer less than or equal to n divided by d is the quotient. Now, once you have the quotient, the remainder is very easy to calculate. You just take n minus d times q. Now remember, you're given n and d, and that's your remainder. Okay, so next we have the Euclidean algorithm, and the basic theorem here is that two GCDs are the same. But first let's talk about the numbers. Let a and b be non-zero integers. There exists a quotient and a remainder that are integers satisfying this, and this is just a repeat of the above result. But what I want to point out, and so we have the same bound here, except I put a less than or equal to sign here and take 1 off of the end. But what I want to point out here is that we have the greatest common divisor of a and b equal to the greatest common divisor of q1 and r. Okay, so when we perform the Euclidean algorithm, what we do is we move the b over to be on the on the left-hand side of the equation. We move the r over, and then we seek a new quotient and a new remainder. And we carry this out until we get a 0 for the remainder, and we know then that we're done, and we can then state that the number above that is going to be the GCD. Okay, and so once you've got the GCD, there's an extended part of this algorithm called the extended Euclidean algorithm that allows you to solve this Diophantine equation. And I need to move this up a little bit now. So it allows you to solve this Diophantine equation right here. ax plus by is equal to d for integers x and y. Okay, so what you do is basically you set a few more things out when you carry out this process. And that allows you to represent your greatest common divisor, d in this case, as ax plus by, where you find those integers, and then therefore you're able to solve this Diophantine equation. Okay, so yes, we use the Euclidean algorithm to find those integers x and y. And finally, we can use our solution to this Diophantine equation to find modular inverses. Okay, so that's what we're going to do. And then in the final part of this lecture, what we're going to do is look at the Chinese remainder theorem, which says, let n1, n2, ... nk be positive integers that are greater than 1 if the GCD of all of those numbers is equal to 1, and this is otherwise called relatively prime, and you have a subscript j between 0 inclusive but less than nj, where the aj are integers, then there is a unique integer x between 0 and n but less than n, where n is equal to the product of those integers, n1, n2 up to nk. There exists a unique integer x such that this simultaneous congruence has a unique solution. Okay, now there's an equivalent algebraic statement, which is to say define a map from integers mod n. Okay, and in our studies so far in these lectures, we've used this notation, z subscript n there. And for these, we've used z subscript n1 cross z subscript n2 cross, and then ... cross z subscript n k. Okay, that's the notation that we've used, but some people use this notation. I just want you to see both notations. Okay, so we've defined a map from integers mod n to the Cartesian product of all of these. That map is given by sending x to x, comma, x, comma, ... comma, x in this ring. Then this is an isomorphism of rings. And remember what that means is that the two rings have the same algebraic structure. Okay, so that's just an overview of the Chinese remainder theorem, or CRT for short. So that's what we're going to study today, those two main topics. All right, and so we'll begin now with the first problem, which is to calculate the greatest common divisor of 19 and 323 using the Euclidean algorithm. Okay, and I've got this written here just to remind us the process. Okay, so what we want to do in order to calculate this greatest common divisor, and I can't properly describe this without showing you an example, so I feel I must. All right, so 323 equals 119. We've taken the bigger one there and put it on the left, times q plus r. Okay, we seek a quotient and a remainder. All right, so what we do now is we divide 323 divided by 119, and we get, let me just do a calculation on my computer. We get 2.714 and so on for just the division of that. So we throw away the part to the right of the decimal point, and we say that the quotient is 2. So 323 is equal to 119 times 2 plus our remainder. But now we can calculate the remainder by taking 323 minus 119 times 2, which is 85. Okay, so now that we have that, what we want to do is a calculation on the side, which is the extended part. Okay, so I'm just going to write extended Euclidean algorithm below on this side. I don't want to put a vertical line there, but I mean on the right hand side. And I'll leave a lot of space over here so things don't get too confusing. All right, so what we want to do is rearrange this equation to solve for 85. So 85 is equal to, now I'll put the smallest number first, so that would be then minus 2 times 119 plus 1 times 323. Okay, I'm putting brackets around these because I want to treat these as if they are variables. Okay, I don't want to add these two things together here. I want to separate them. All right, so next, remember what we do is we bring this 119 over. And then we say that that's equal to bringing the 85 over, 85 times Q1 plus R1. And we've taken that 119 over, we've taken the 85 over, and we seek a new Q and a new R, a new quotient and a new remainder. Okay, so 119 divided by 85. That gives us 1 point something, but we're only interested in the 1. So we have 119 is equal to 85 times 1, and then plus the remainder, which is the difference, 119 minus 85 times 1. Okay, that's 34. So we've got a new remainder there is 34. Okay, so next what we want to do is write 34 in terms of 119 and 323. So 34 is equal to 119 minus 85. Okay, I'll put the 119 first. So we'll say 1 times 119. And then we've got plus minus 1 times 85. But I'm going to take this 85 and substitute what I have up here. Okay, I'm going to substitute it in and then collect like terms where I'm thinking of the 119 and the 323 like variables, right? And that's why I say collecting like terms. I don't want to sum it all up. I want to treat those like variables here. Okay, now we need a little bit more space to make this substitution. So 1 times 119, and then we have plus minus 1 times what we have here. Okay, so minus 1 times minus 2 is plus 2 times 119, and minus 1 times minus 1 is minus 1 times 323. Okay, now collecting like terms, we have 3, 1 plus 2, we have 3 of the 119s. So 3 times 119 plus minus 1 times 323. Okay, and this was 34. All right, so the process, this part of the algorithm being the extended part of the algorithm, this allows us to solve the Diophantine equation 119x plus 323y is equal to our greatest common divisor. Right, so when we get down to the end, we'll have the greatest common divisor here, and then this will be our x and our y. Okay, but we're not there yet. Okay, so next we want to bring the 85 over. So 85 is equal to 34 times a quotient 2 plus a remainder 2. We've taken the 85 there and the 34 there. Okay, now we seek our new quotient here. In this case, let's see, it's probably about 2. So 34 times 2 is 68. But if we have a quotient is 3, that would be too high. So we'll say 85 is equal to 34 times 2. And then the difference between 85 and 68 is 17. Okay, so now I want to rearrange this and say 17 is equal to, let's see, what have we got? Minus 2 times 34. and then plus 1 times 85. Okay, now we have identities for 34 in terms of 119 and 323, and for 85 in terms of 119 and 323. So we want to sub both of these in here and collect like terms in terms of 119 and 323. Okay, so let's do exactly that. Now 34 is this one right here, but we want to multiply the minus 2, distributing it over the addition, and say that minus 2 times 3 is minus 6. So minus 6 times 119. And then minus 2 times minus 1 is plus 1 times 323. And we do the same thing with 85, but we've got a 1 in front, so it's just plus minus 2, copying from here, times 119, and then plus 1 times 323 from there. Okay, now we collect like terms, and we see that minus 6 minus 2 is minus 8 times 119, and then 1 and 1 is 2. Actually, have I missed something? I think I have a mistake here somewhere. I think this should be a 2. Is it? So we subbed in 85. Okay. So 85. No, I believe that's right. Okay, good. Okay, so then we have 1 and 1 is 2 times 323. And I better check this because I had some doubt there. So I'll get on my computer and check this. So 323 times 2 minus 8 times 119 is not quite right. Okay. So 3 times 323, yeah, so this is meant to be a 3 here. So up here, or is it? I do here. Anyway, there's a little error in there somewhere. Something's meant to be a 2 rather than a 1. Okay, so this works out correct. Okay, and this is 17. Okay, so now that I have that, I want to continue the ordinary part of the Euclidean algorithm, which would be to take the 34 over, and then I bring the 17 over, and then I seek a Q3, and then plus an R3 for the third remainder. Okay, so I've brought this over, I've brought this over. Now this is simple to see because 34 divided by 17 is 2. So 34 is equal to 17 times 2. And then we have plus 0 as our remainder. Okay, so this tells us we're done because we got 0 there. So this, above it, the last remainder, must be the GCD. So GCD of 119 and 323 is equal to 17. Okay, now notice what we have here, right? If we call this D, we have a solution xy in integers to the Diophantine equation. Uh, 119 x plus 323y is equal to 17. Okay, this is our greatest common divisor of 119 and 323. So we've actually solved this. Here, x and y are -8 and 3. Okay, so we've got this, but since 17 divides into 119 and 323, we can actually do that division, and we find that 119 divided by 17 gives 7. So we also have solved 7x plus 19y is equal to 1, because 323 divided by 17 is 19. Okay, so this is great because this will allow us to find an inverse of, say, 7 modulo 19 and 19 modulo 7 via reduction. So that brings us to the next page, where I've got a question that says find the inverse of 7 multiplicatively modulo 19. Okay, now we know that that should exist because 19 is prime, and so the GCD of 7 and 19 is equal to 1. Okay, now to do this, we note that 7x plus 19y equals 1 reduces to, now we want to reduce mod 19, reduces to 7x is congruent to 1 mod 19. All right, and so we're seeking x now, but we've already got x, so we already know from extended Euclidean algorithm that x is -8. Okay, so if we reduce this -8 modulo 19 so that we get a number between 0 and 18, well then all we would be doing is adding 19 to this. So 19 minus 8 is equal to 11, which is less than 19 and greater than 0. So that will be a good representative. Okay, so x is equal to 11 is our modular inverse. So we'll say 7 inverse is equal to 11, or congruent to 11 mod 19. Okay, now let's check this. So 7 times 11 is 77. Okay, now let's take out all of the multiples of 19. So 77 minus 19 is 58. 58 minus 19 is 39. Okay, if we take out another 19, we get 20. And if we take out another 19, we get 1. Okay, so in other words, this is 4 times 19 plus 1. And so this is congruent to 1 modulo 19. Okay, so we found a multiplicative inverse of 7 in integers mod 19. Okay, next let's have a look at the Chinese remainder theorem. But for this, I'll pull up the notes that I had on the Chinese remainder theorem. Okay, Okay, so remember, if we have relatively prime integers n1, n2 all the way to nk that are greater than 1, and aj between 0 and nj but less than nj, then there's a unique integer x between 0 and n, where n is the product, such that this simultaneous congruence is satisfied. And there's an equivalent algebraic statement saying that there's a ring isomorphism between integers mod n, uppercase n, which is the product, and the Cartesian product of all of those divisors of uppercase n. Okay, so let's go ahead now and have a look at this problem. Solve the simultaneous congruence. X is congruent to 2 mod 3, and x is congruent to 4 mod 5. Okay, so we see that the GCD of 3 and 5 is 1, and the product of those two is 15. So uppercase n is 15 in this case. Okay, so we want to just check through all of the integers from 0 up to 15 minus 1. So check x equals 0, 1, 2, up to 15 minus 1, which is 14. Okay, but if you check all of these, you can see, well, 0 doesn't work, 1 doesn't work, 2 doesn't work. 2 works in the first one, but not the second one. 3 doesn't work, 4 doesn't work. 4 works in the second one, but not the first one, because 4 is congruent to 1 mod 3, which is not 2 mod 3. 5 doesn't work, and so on and so on. Finally, you get up to 14. 14 is the only element of integers mod 15 that satisfies the simultaneous congruence. Okay, now let's check. 14 is congruent to 2 mod 3 because 14 is equal to 2 plus 12. 12 is 4 times 3. Okay, 14 is congruent to 4 mod 5. 14 is equal to 4 plus 2 times 5. Okay, so bingo, 14 works. So now exhibit a solution in the Cartesian product of Z3 and Z5. Okay, so we should have 14 comma 14, but this is the same as 2 comma 4 in Z3 and Z5. Okay, and we see the 2 and the 4 right there. All right, now show that we have solved the matrix equation 1 minus 3, 0, 1, 0 minus 5x is equal to 2, 4 for triples of integers. And note that this can be solved by the Hermit normal form, and I'll talk about that in a moment. All right, so what we would be doing in solving this congruence up here is solving a simultaneous system of equations. X is equal to 2 plus 3y, and x is equal to 4 plus 5z. Okay, so this is our system of equations that we want to solve in integers. So we could call that a Diophantine system of equations. Now if we rearrange this, we can write this as x minus 3y is equal to 2, and x minus 5z is equal to 4. Okay, and this system can be written as a matrix equation. 1, minus 3, 0. 1, 0, minus 5, and then times x, where x here is x, y, z, the column matrix. And so this is equal to 2, 4. Okay, so we have a corresponding matrix equation here. Now, you know that you can reduce matrix equations using Gaussian elimination, right? But you do that when you are interested in real solutions x, y, z. Now, when you're interested in integer solutions x, y, z, you use what's called the Hermit normal form, which is essentially the same process, except for you don't want to be dividing, right? So you need to leave your pivots as whatever positive integer you end up with. You don't want to divide by those pivots to get 1. All right, I'll just grab some more paper here. Okay, so now the Hermit normal form, so HNF for short, so that's an algorithm, but it would find the matrix 0, 1, minus 1, 1, belonging to GL2 Z. So it's got integer entries, it's invertible, and basically what we have then is we're able to multiply this on the left. So multiply by, and let's just give this the name A. Multiply by A on left of the equation. So we have 0, 1, minus 1, 1, 1 minus 3, 0, 1, 0, minus 5, times x is equal to 0, 1, minus 1, 1, times 2, 4. Okay, so when we multiply that out, and so this will give us the equivalent of row operations here. So when we multiply this out, what we get is 1, 0, minus 5, 0, 3, minus 5, x is equal to 4, 2. Okay, so this here is in Hermit normal form. We have pivots. We have zeros above our pivots, 0 below the pivots. So these two are pivots there. We cannot divide by the 3 because then we would have fractions, and we have to avoid this here because we're seeking integer solutions. Okay, and this just gives us an equivalent way to look at the equation. So we have x equals 4 plus 5z, and y is equal to, 3y is equal to 2 plus 5z. Okay, so this could make the process easier of seeking an x. Right, so for example, if we try z equals 1, it doesn't work because 2 plus 5 is 7 is not congruent to 0 mod 3. If we choose 2 for z, we have 4 and 5 times 2 gives 14. 2 plus 5 times 2 gives 12. That is divisible by 3. Okay, so z equals 2 gives x is equal to 14 and y is equal to, let's see, what did we say? 4. Okay, next we're going to consider polynomial greatest common divisors. So consider the greatest common divisor of two polynomials f and g, and suppose that's equal to d. So what this means is that f is equal to d times some polynomial h1, and g is equal to d times some polynomial h2, and every common divisor of f and g divides into d. Now this is only possible in a unique factorization domain, which we abbreviate as UFD. For example, the ring z adjoin x, so polynomials with integer coefficients, or for example, polynomials with coefficients in a field. A unique factorization domain is a ring with unique factorization. So it's a ring. Okay, now if we have f of x is equal to u times polynomial 1 times polynomial 2 times dot 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 times polynomial n, this is unique where pj are irreducible, meaning if you try to factorize them, you only get themselves. And u is a unit. Now remember, we talked about units in our previous lecture being invertible elements. So a unit in zx, but the only units in zx are plus or minus 1. Okay, so this is unique, meaning that we have a unique factorization domain. Now, an example of a not unique factorization domain, which is a ring, is integers adjoin the square root of minus 5. Now, previously we talked about the ring integers adjoin plus root 5, or the square root of positive 5. Okay, these are not the same rings. Now this is, so z adjoin root minus 5 is the set of all a plus b root minus 5, where a and b are integers. Now for this particular ring, only plus or minus 1 are the units of this ring, whereas the integers adjoin root positive 5, that has infinitely many invertible elements or units. Okay, so the only units of this are plus or minus 1. Now consider the two factorizations. 6 is equal to 2 times 3, but 1 plus root minus 5 times 1 minus root minus 5 also gives 6. So we have two factorizations, but the key here is that these numbers are not different by multiplication by a unit, because the units are only plus or minus 1. So that makes this factorization here not unique. Okay, so this is an example of a ring that's not a unique factorization domain. Okay, so given this, we can also perform a Euclidean algorithm on polynomials. So let's have a look at this example that I have here on the right, which says find the GCD of f and g where f of x is 2 plus x cubed, and g of x is 6 minus 3x plus 7x squared minus 2x cubed plus 2x to the fourth. Okay, so again we want to write 6 minus 3x plus 7x squared minus 2x cubed plus 2x to the fourth is equal to 2 plus x cubed times q of x plus r of x. And we want to find this quotient and remainder. Okay, so now I hope you remember long division, because that's what I'm going to do here. I'm going to do a long division with these polynomials. And here I'm going to place this one, but in reverse order to make this easier for me as a human. Okay, now I'm looking for a polynomial that when I multiply by x cubed, I get 2x to the fourth. So in this case, 2x will do the job. Okay, now I multiply this 2x by this polynomial here on the left, and so I get 2x to the fourth for the first term. Then I get 2x squared, but I'll put that over here under the x squared term there, and then plus 4x. And that's it. Now I draw a line and I take a difference. Okay, so I've got 0 for this difference. Then I have minus 2x cubed. Then I have 7 minus 2 is 5. X squared minus 3 minus 4 is minus 7x. And then I bring down the 6. Okay, now I do this again. So this time I need a minus 2. Okay, so minus 2 times x cubed is minus 2x cubed. Then minus 2 times x, I'll put that over here, is minus 2x. And then minus 2 times 2 is minus 4. Take a difference. Minus 7 minus minus 2 is minus 5x. Okay, bring down the 5x squared, and then the difference of these two is 0. So I have 5x squared minus 5x plus 2. All right, now this is my remainder here. So I have 6 minus 3x plus 7x squared minus 2x cubed plus 2x to the fourth is equal to 2 plus x cubed times 2x minus 2 plus the remainder 2 minus 5x plus 5x squared. Okay, so now we want to shift these over just like we did earlier with the integer version of the Euclidean algorithm. So I'll put now 2 plus x cubed equals, now I want to bring this remainder over, but I notice that I've got a 5 in front of the x squared term there. So, and hang on, oh, that difference is 10. Okay, 6 minus minus 4 is 10. I knew that didn't look quite right, so that's a 10 there. Okay, so everything's divisible by 5 here. So I want to factor out that 5 and write 2 minus x plus x squared, and then put 5q1 plus r1. So these are of x and of x. Okay, good. Now what I want to do, because if I do a long division here, I've got this 5 in the way, so I really want to do the long division with these two. Okay, so the way I set this out now is I put x squared minus x plus 2, and then I put x cubed plus x plus 2 there. Okay, now I need an x there. X squared times x gives x cubed. So I put an x here. Then I multiply this times all of this. So I get x cubed minus x squared plus 2x. Then I take a difference. So now I have x squared plus x minus 2x is minus x. And then I bring down the 2. So I can actually get rid of this one there. Okay, so what I have then is that 2 plus x cubed is equal to 2 minus x plus x squared, taking this, multiplied by, alright, and this, actually I haven't finished that because there's a plus 1 there, and then I take a difference, right? Okay, yeah, I'm just seeing that those two are the same, but I really need a plus 1 here. Then multiply that out and take its difference, and I get 0. So I have a 0 remainder here. Okay, so I've got my Q1 is x plus 1, but I have a 5 in front. So then I should have 5 plus 5x. And then I have plus 0 there. So that says I'm done. And the greatest common divisor of f and g is equal to, well, the thing I have above it, but I need to factor out the 5. So I have 2 minus x plus x squared as my greatest common divisor there. Okay, and so yeah, and there, of course, there's a Euclidean algorithm, an extended Euclidean algorithm to go with this as well, to be able to solve what is the analog of a Diophantine equation, a linear Diophantine equation involving the f and the g, and the GCD, of course. Okay, that's all I have for now. I'll see you in the next one.